Hey there, welcome to your next video tutorial right after how to verify an exact differential equation. Now in this video, we are going to find the solution to an exact differential equation. You see, it's a gradual process, alright? So, solution to an exact differential equation. And I promised you already in our previous video that I'm going to give you some steps that will guide you in solving or in deriving a solution to an exact differential equation. But don't forget, the solution to exact differential equation is in the form u, which is in terms of x comma y is equal to c. That is a general solution to an exact differential equation. So, how do we derive that? Let's look at the first step. The first step is to check whether, or I would say, is to check our previous video, if that is true. So, if you haven't watched our previous video, please, I would like you to go back and watch it. So, you need to first check whether the partial derivative of n as respect to y is equal to the partial derivative of n as respect to x. And if that is established, then you now go and find the function of u in terms of x and y. Because we want to find the function. In fact, all that we are doing is to find the total derivative. Is to find u in terms of x and y, so that we can equate it to the c. Alright, so we now go and find this. And the first thing to do is to take the partial derivative of u as respect to x. The partial derivative of u as respect to x. Don't forget that in the question you will be given this. You will be given this, alright? So for this, there you go. First, check whether this is exact. If it's exact, then you continue to find the function of u in terms of x, y. So in doing that, we need to go and find the n. And the n is the partial derivative of u as respect to x. And the n is the partial derivative of u as respect to y. Please be careful. How to check the exactness is not the same as finding this and this. Look at the difference. This is the partial derivative of n as respect to y, but this is the partial derivative of u as respect to x. We have already done that, we have already established that, so please don't be confused yourself. Alright, this is never the same as this. This, I repeat, this, finding this is not the same as this. Alright, let's move on. So, the function of u in terms of x and y is going to be equal to. So after getting this, you are going to get this to be a function in terms of x and y. This one will be a function in terms of x and y. I'm taking my time to explain to you well. Alright. So to get the function of u in terms of x and y, you need to integrate. Now it's whether you go for this or this. We have two alternative way here. Alright. The second step is giving you the first method. And the third step is giving you the second method. So what is the first method? Now, if you are used to integrating as respect to x, that means that you pick the function n. Because that is the total derivative, the partial derivative of u as respect to x. So you pick that one, then you integrate as respect to x. So when you are integrating this function, which is in terms of x and y, as respect to x, in the same way, what we do in the derivative, we do the same thing in the integration. What do we do in derivative? When you are taking a partial derivative of a function as respect to two variables, you treat one of the variables as constant. So if you are having this n to be in terms of x and y, and you are integrating it as respect to x, you treat y as constant. So you are going to treat y as constant. So definitely, and you know that after integration, you add plus c. Now, the c here is representing the family of terms. But here, we don't bring the plus c. Because we are saying that since we are integrating as respect to x, we treat y as constant. Therefore, your constant is y. And it's not going to be just y, but rather it's a function of y. It's a function of y. So whether you write g of y, h of y, or whatever, anyhow you want to do it. But I prefer you do it this way. The second step, the third step is the alternative way. Now, somebody can choose, no, I'm not used to, somebody will say, no, I'm not used to integrating as respect to x. I'm used to integrating as respect to y. No problem. You can do that. You can do that, alright? But what you do here, where is it? You are going to find the n. So this is the same thing. You find the n, where the partial derivative of u as respect to y, you see the same thing. Then the partial derivative of u as respect to x, that gives n. This step, this is the same thing. But with this, you find this. This is different from the one here. Watch. Here, you take the integral of the function of n, which is in terms of x and y, as respect to y, but not x. And don't forget, since we are taking it as respect to y, we are going to get our constant to be x. Because when you are integrating as respect to y, you treat x as constant. So you are not just going to get x to be the constant. You say after integration, I add plus x because the x is the constant. No, it should be a function of constants or a family of constants. So that will be the h of x. Here we replace a g of y here. That is why you are replacing h of x. Please, I hope it's clear. For the first, second, and the third. So, for me, I'm used to integrating as respect to x. So, if I'm to be you, I will go for the second one. But hey, please, I can't force you. Go for the one that you like. Alright. So, it's whether you are picking step 1 and step 2, or step 1 and step 3. But you can't pick both. Never. Fourthly, then you solve for g prime of y or h prime of x. All means that whether you are going by this or this. Alright? So there's one more thing I think that is there should be something before this, alright? And I want to bring it here. I would like to bring it here. Now, when you are done with this, when we are solving a question, it will reflect very well. That's why I didn't show you the steps, but don't worry, I want to help you with it. Alright? Now here, it depends on you. When you take the integral of the function of m in terms of x and y, then the results that you're going to get here, or whether you go by this, the results you get here. So I'm going to base on this. The results that you're going to get here, don't forget, it's m that you take the integral as respect to x. So this is free. So you now go and find n. That should be the next step, n. That's the partial derivative of u as respect to y. You now go and take the result that you're going to get here. You take the partial derivative of this u as respect to y. when you integrate, are you watching? When you integrate as respect to x, the results you get, watch, the results you get, you now go and take the partial derivative of the results as respect to y. When you integrate as respect to x, you go and take the partial derivative of the results of your integral function as respect to y. And when you integrate as respect to y, you now go and take the partial derivative of your integral results. You now go and take the partial derivative as respect to x. So if you pick this, you take the partial derivative as respect to y. But when you pick this, you take the partial derivative as respect to x. It's very clear. It's very clear. Alright. So that is why the G prime and the H prime will come in. The reason is that when the second step, when you differentiate this, or when you take the partial derivative of the results as respect to y, you are going to get the integral function plus G prime of y. Because we now go and differentiate this. So this will be G prime of y. And when you integrate as respect to y, you go and take the partial derivative of the integral function. You now go and take the partial derivative as respect to x, and that will give H prime of x. It will be something plus H prime of x, depending on the question. Alright. So that is why the fourth step, please, I hope you are following. That is why the fourth step. In fact, this video is what a lot of you are waiting for, and I'm taking my time to explain to you. So the fourth step is, that is why he's saying that solve for G prime or H prime. Where is the G prime and the H prime is coming from? It's coming from after taking the partial derivatives of the integral results. Because we don't have any H prime and G prime here. We don't have any H prime or G prime here. So that is where it is coming from. Fifth part, integrate. So for you to solve for this or this, depending on the one you choose, you now integrate. Because when you integrate both sides, you undo the derivative. So when you integrate, then you integrate to find G of y or H of x. Sixth part, replace G of x or H of x from 2. So looking at the second step, it's whether by depend whether you go by this or this. So 2 or 3. So after getting G of x here, then you're going to replace it here. And don't forget that we are looking for a function of u in terms of x and y. So when you replace G of x or H of x here or here, you are going to get a function of u in terms of x and y. Hope it's clear. Alright. The 8th part is talking about initial value. That one is depend whether an initial value is given to you or not given to you. So you end your solution by equating this to C. Alright. And when initial value is given to you, you can now get the C and do the substitution back. In fact, I have talked a lot. I have taken my time to explain it a lot. And if you are still not getting it, don't worry. You can play back the explanation to the steps again. And I'm now coming to solve a question for us to see clearly what I was struggling to get you understand. Alright, welcome to our first question. Now, we have to find the exact differential equation of the following. So, for now, I'll give you the first one. So, this is our first question. In fact, I love it. The first thing to do is what? Yes, exactly what you are thinking of. Is to check whether the differential equation is exact or not. Alright. Because if it's not exact, you can't solve it. And that will come after we are done with this. In case it's not exact, then how can we do it? Let's see. So the first thing is to identify whether it's exact or not exact, or is to verify. Alright, so we know that here the one attached with this ds is the m. We use the m, which is 4s minus y. Then we take the partial derivative of m as respect to, hope you haven't forgotten it. That is not as respect to x. In fact, it's a problem for most people. It's as respect to y. That is the opposite of what you are thinking of, that it is attached to ds. So we treat s as constant, so this will be -1. Then we go for n, which is in terms of s and y, and that is n is attached to the y, so that is 6y minus x. So the partial derivative of n as respect to opposite of what you are thinking of. So we treat y as constant, so this one is 0, so we get -1. Beautiful. Beautiful. Why is it beautiful? Because the partial derivative of m as respect to y is equal to the partial derivative of n as respect to x. So since this is equal to this, then we are saying that is an exact. It's an exact. Then if so, this is the first step. Second step, if it's exact, then let's go for the solution to it. So the second stage is for us to find, that is what we are going to find. And how do we find that? We need to find the total derivative of u as respect to x. Then we go for total derivative of u as respect to y. But one will represent n and the other will represent x. And how do we choose? People think that since this is as respect to y, so the one as respect to y here will be the m. That is a lie. That is a lie. But rather, the one that we are taking as respect to x is rather our m. And this is rather our n. So that is how we find the total derivative from our first video of what is exact differential equation. You can go back and watch. So the n is the partial derivative of u as respect to x, and the n is the partial derivative of u as respect to y. That is how we find the total derivative. Please don't confuse yourself to it with verifying the exact differential equation. That is not so. Alright. So we know our m is this, our y, our m is this, our n is this. In fact, because of confusion, I would like to repeat that again here. Oh, I should have written it before. Because I don't want you to confuse yourself. I will waste my time to repeat it again. So this is 4x minus y. So you take, and the n is 6y minus x. So you take the partial derivative of u as respect to x and partial derivative of u as respect to y. But one represents n and one represents y. So this represents the m and this represents the n. Alright. So that is what we mean by that. And we are saying this is not the same as this. Alright. So now let's move on. Here, what do we do? That is taking the derivative of this by treating y as constant. So when we treat y as constant, that means that this will be 0. So here we are going to get 4. I'm coming. Oh, sorry. We are not going to take any partial derivative of u as respect to x. Now, you know that this is a total derivative. And if it's a total derivative, you know that is in the form the partial derivative of u as respect to x dx plus total derivative, partial derivative of u as respect to y dy, which is equal to 0. So we are saying that this is in this form. And if this is in this form, then we can say that the partial derivative of u as respect to x is the same as the m. And that is 4x minus y. I hope you're not confused. Very good. And the partial derivative of u as respect to y, which is the n, is 4x minus y. Oh, sorry. That is 6y minus x. So here we are not to take anything. We are just coming from this part that this represents this represents this, and that is the same as m, and that is the same as n. Alright. So that is the second part. That is the second part. And with the second part, we need to do the last thing. And that one is whether you go for the second part or the third part. Here is when I said we have to find, don't forget to find this. So if you want to find this, you need to first identify this and this. And after that, this the function of u of x and y is going to be the integral. So here is when I was saying that are you used to integrating as respect to x or used to integrating as respect to y? For me, I'm used to integrating as respect to x. So I'm going to pick this. So I pick 4x minus y and integrate as respect to x. Alright? So I'm going to integrate this as respect to x. And what is that going to give me? Now, when you are integrating this, oh, you can also go for this, okay? But please, let's stick to one thing. To integrate this, you get 4x squared over 2 minus, we are treating y as constant. Since we are integrating as respect to x, we treat y as constant. So you know that whenever you integrate a constant, you add a variable that you are integrating as respect to its weight. So here it will not be 0, it's not differentiation. Here it's going to be sy plus the constant, and the constant here is y. So it's going to be family of y. Very good. So that is what we are going to get for the second part. And the second part, we are not yet done. We need to do the next thing before we go to the fourth part, where we find G prime. So we pick this to integrate to get this. Please watch here very well. You pick this to integrate to get this. Now, we are going to pick this because while you pick this to integrate as respect to x, then you pick this to differentiate as respect to y. So we are going to take the partial derivative of u as respect to x. Sorry, as respect to y. As respect to y. And it's not that we are going to take the partial derivative of u as respect to y of this function, but rather the results, that is almost the confusion of some students, is of the results. So you just pick this, integrate as respect to x, leave it. Then you come back and write this. You just quote this here. And what this means is that you are going to differentiate this as respect to y by treating s as constant. So you know that this is going to give you 2x squared. 2x squared. Very good. So here we are going to treat s as constant. So this will give you 0 minus, since we are differentiating as respect to y by treating s as constant, then we get negative x plus. Don't forget, when you differentiate this, you are going to get g prime of y. So here is where the g prime of y is coming from. We are still not going to step 4. Here, what we have here is that you just quote this. Or another thing that we can also say is that after integrating this as respect to x, the results you get, take the partial derivative of this u as respect to y. And now, the partial derivative of this u as respect to y is exactly what we have here. So we know that this left-hand side is equal to this. So we equate 6y minus x. Hope you can see that. To be equal to negative x plus g prime of y. And no matter what you like, no matter what, something will cancel out here. If you equate this to this and nothing is cancelled out, please go back and recheck your work. So here you can see that this will cancel this, because when this comes here, you get minus x plus that. So that one will cancel. So we are going to get finally g prime of y is going to be equal to 6y. That is why, go and check the fourth step. That is why the fourth step is insisting you to, or is directing you to find g prime of y. So you see, right after the integration, you take the partial derivative of u as respect to y, because you integrated as respect to x. But when you integrate as respect to y, that means that you are taking this. When you integrate as respect to y, you come and take the partial derivative of u as respect to x. Hope you can see that. Very good. So now we have this. So the fourth step. Please, I would like to clean this part. Alright. So this is the third step. Let me show you the third step. All this is the third step. This is the third step. This is the third step. We did not go for the third step. That is integrating as respect to y. So this is the third step. So let's jump the third step and go to the fourth step. Fine, get an understanding, not by the step. But that one too is very helpful. So the fourth step is to find, it's for us to find g prime of y. So let's go and find g prime of y. And how do we do that? That is why the fifth step is saying that integrate as respect to y is equal to integral of 6y as respect to. So this bring back the function. Then when you integrate this as respect to y, you get 6y squared over 2, which is 3y squared. Very good. So we now get g prime of y equal to 3y squared. So you can see, all that we are doing is to find the solution to an exact differential equation, and that is the function of u as respect to x and y. But after integrating this as respect to x, then we come out that this one here we have to go and look for x. That is why we are doing all these things. So we now have g prime of y. So all that we are doing, we are going to do for now is that we're going to replace. We are going to replace. That's why the seventh stage or the C stage is telling you to do that. So we replace that by this. So therefore, u of x comma y is going to be equal to 2x squared, quoting from here, minus sy plus, now instead of writing g prime of y, I'm going to write 3y squared. So, but wait, that is the function, but this doesn't mean that what we have here is the general solution. You know that the general solution is in the form this. So we now equate, so but this is equal to this, so C is equal to 2x squared minus sy plus 3y squared, or plus C. So here is, equal to C. So it's here when that in case an initial value is given to you, then you go and do the substitution to get C and come and write it back. So see you for the next question. That is the question 2. Alright, so we are back. Let's look at our second question under exact differential equation. So we have to show that the following equations are exact and solve them. Okay, so the first thing to do is to show whether it's an exact or not. And even if you are not asked to show, whether you like it or not, you show before you solve. So the first thing to do is to check whether it's exact. How do we check whether it's exact or not? Very good. So we identify our function of m in terms of x and y to be x to the power 3 plus y over x. Then n is equal to that is y squared plus ln x. Ln x. Very good. So now with this, then we take the partial derivative of m as respect to y. We take the partial derivative of n as respect to y. But don't forget, if you are differentiating as respect to y, that means that you treat the x as constant. So when you treat x as constant, then look at what you're going to get. This is a constant, so when you differentiate this, you get 0. But watch. 1 over x times y. This is the same as this. So when you are differentiating as respect to y, you treat the whole this as a constant. And when you differentiate y, what will you get? That is 1. And 1 will multiply 1 over x, which is 1 over x. Very good. So here we are going to get that. Then we go and take the partial derivative of n as respect to x. As respect to x. Here we treat y as constant. So this is going to give you 0. Alright. Then linears. When you differentiate linears, what will you get? 1 over x. That is why you don't need to forget your calculus 1 and 2. Alright. So now you can see that the partial derivative of the n as respect to the y is the same as the partial derivative of n as respect to x. Therefore, we are saying that this differential equation is an exact differential equation. After showing that it's an exact, then you move on to solve. And how do we solve it? First of all, this is where the confusion starts. The exactness is done. We are now coming to solve. So when you are solving, you have to identify, because this is coming from a total derivative, which is the partial derivative of u as respect to the partial derivative of s dx plus the partial derivative of u, the partial derivative of y dy, which is equal to 0. Now, this differential equation given you here is in this form. Therefore, the partial derivative of u as respect to dx is this, because that's the one attached to the one, to the x. And the total derivative of u as respect to y is this. And we are saying that this is the same as m, and this is the same as n. Hope you are getting it. Very good. I trust you. I said I trust you. Don't fail me. Make sure you understand. Alright, so the partial derivative of u as respect to x is going to be the function of n, and that is y squared plus s. Very good. Very good. Now, having this, then we move on to identify or to find, that is the second stage. Alright? The third stage is there, but it's whether you pick the second stage or the third stage. Here we are going to find the function of u as respect to x and y. Alright. So here, that is when you have to take your time. Alright? If not, you mess up. This is when you have to take your time. Now, it's whether you want to differentiate as respect to x or you want to differentiate as respect to y. Okay? Very good. Sorry, integrate as respect to s or integrate as respect to y. But we are used to integrating as respect to x, so let's go by that. That means that you pick this. When you pick this, it means that you are integrating as respect to s. When you pick this, it means that you are integrating as respect to y. But let's pick this. Hope you can see that. Very good. So, here, all right. Okay. So when you integrate this, what are you going to get? You get x to the power 4 over 4. plus. Now we are integrating as respect to x by treating y as constant. So when you are integrating this by treating y as constant, watch. You are integrating y over x, which is the same as. If y is a constant, you can bring y out, so the one will be here. So this is going to be ln x. So you are going to get y ln x. Very good. Time for us to be confused. Because the constant is y, so we can bring the constant out and integrate 1 over x, and that is y ln x. Very good. Now, anytime after integration, we add plus c, but here we are saying that we are treating y as constant. So, our constant here is going to be g of y. So this is u x, the function of u in terms of x and y. Right after integrating this as respect to x, that means that you are going to differentiate the integral function here. You are going to get the total, then you are going to take the total derivative of u as respect to, don't forget, you integrate as respect to x. So you take the partial derivative of u as respect to y. And that is exactly what is here. And that's exactly what you left here. That is the part you didn't integrate. And when you are differentiating this as respect to y, that means that we are treating s as constant. So the whole of this is 0. Alright? Now when you get to this side, this s is a constant, so that is a constant. And when you differentiate this, you get 1, so you get that place to be ln s. Plus, when you differentiate this, you get g prime of y. Very good. Now watch what you're doing. Know that the partial derivative of u as respect to y is exactly what is here. Therefore, we know that this left-hand side is y squared plus ln x. So we replace y squared plus ln x. Then we equate it to ln x plus d prime of x. In fact, as I told you, always, when you equate this to the derivative of the integral function, definitely something must cancel out. Something must cancel out. If not, then you are messing up. Alright. So you can see that when this comes here, this will cancel this. And what do we have now? We are done with this part. And what we have now is g prime of s, which is equal to y squared. Now, don't forget, we are looking for this. But because of this, that is why we continue to take the partial derivative of u as with respect to y in order for us to get g of x to come and do the substitution here. So we are looking for this to completely get our equation. So here what we do is that to get g of x, we undo it, alright? We need to undo it. Are you sure it's x? It's y. It's supposed to y. So here we get g of y is equal to y raised to the power 3 over 1 over 3. Don't add any plus c. So now what we have here means that g of y is going to be equal to 1/3 y cubed. So you come back and rewrite this, but wherever you see g of x, put this there and you are done. Oh, is it difficult? I will not show you difficult. Never and ever. So finally, we get I have to quote, and that is clear also. I have to bring it back. So this is equal to x to the power 4 over 4 plus y in s plus, don't forget, y raised to power 3 over 3 is equal to c, because the general solution is this is equal to c. So therefore we get s to the power 4 over 4 plus y in s plus y raised to power 3 over 3. Because so that becomes our final answer, and that is the general solution for the differential equation. Alright, so let's move on to the third question. Alright, so let's look at our third example. So first of all, let's show whether it is exact or not. So this is our m, and this is our n. So the n is the one attached by dy, and the m is the one attached by dx. So let's take the partial derivative of m as respect to y by treating s as constant. So we know this is going to give us 0. But here we have y e raised to power xy, right? Very good. Now with this, if you want to differentiate this, or you want to take the partial derivative of y e raised to the power xy, this is a function, and this also is a function. Now we are treating s as a constant. So this s is like 2y. So if you are differentiating this, you have to apply what? A product rule. This is a product rule, no matter that here is x. If there is no y here, then you can say this is a constant. But since this is attached, it's a function. Alright. So leave this. Then you differentiate this. And when you do want to differentiate this, the constant will drop down. Then we have this, in case you have forgotten small of your algebra, plus okay. So you leave this, then that's the product, then you differentiate this. You differentiate this. When you're differentiating this, the constant will come and multiply by the whole of this. Alright. Plus here you differentiate this, you leave this, then you differentiate y, which is 1. So you are going to get something like this. Alright. So finally we get e raised to power sy, then sy plus 1. So that is what we are going to get for that. Then we go to the partial derivative of n as respect to x. As respect to x. You know that this is a constant, so that is 0. But this is a product rule. So we leave this, then we differentiate this. Here we are treating y as constant, so the y will come here. So we get something like this. Plus, then we leave this to differentiate this, so we get e raised to power sy. So here we get e raised to power sy 1 plus 1 plus x y, 1 plus x y. So in fact it's exact, because the partial derivative of m as respect to y is the same as the partial derivative of n as respect to x. So this is an exact differential equation. And now, if it's a exact differential equation, then how do we solve it? All right. So I would like you to continue with our next step in finding u x comma y. Let's go and do that. But I always encourage you to re-quote everything again. That the f we have here is the same as partial derivative of u as respect to x, not y. To be equal to Alright, so I like you to quote it in this way. And now start with it. Alright, so here, there we go. And find u in terms of x and y, which is the integral of, as I said, whether you want to integrate as respect to x or y. If it's as respect to x, then go for this. We are used to as respect to x, so let's go by that. Then this is going to be called, here we are treating y as constant, okay? Don't forget, as respect to x, so this is 1, so you get x plus. We are treating y as constant. So we are treating this as constant. So how do we integrate this? Y is a constant, so it will come. Don't forget, the constant here is y. So when you are integrating this, the constant e will be divided, and the whole of this will repeat, and the whole of that will be repeat, plus constant of y. So here we are going to get s plus e raised to power sy plus g. Please don't confuse yourself with the partial derivative of this. Is k plus 1. Alright. So this is what we have. Then we are saying that this is what we are looking for, but because of this, we can't leave it as such. We have to go and find that. And how do we find it? Now we now take the partial derivative of this u as respect to y, because we have integrated as respect to s. So you take the partial derivative of this as respect to y, and that is going to give you will treat s as constant. So this is 0. And this, you are treating s as constant, so the s will come here, e raised to the power sy plus g prime of y. But don't forget that the derivative of u as respect to y is exactly the part you didn't integrate. So you now come and equate 2y. Please, I'm just quoting this from here. Is going to be equal to s e raised to power sy plus, and in fact, something must always cancel out. Alright? Something must kill a man. And we are going to get g prime of y is equal to 2y. Then we integrate to do this as respect to y, as respect to y. So you get the function back to be equal to 2y squared over 2. So we get y squared. Very good. So now that we have that to be y squared, then we come and do the substitution back to what we are looking for. Alright? So I'm going to edit my writing. But if you can't edit it, you have to read quotes that then this is equal to that. So I'm going to edit. So instead of this, we ignore g of y, which so that is y squared. But we know that this should be equal to c if only you are finding the general solution. Here we don't know the what we call it. We don't know the interval or the initial value. Alright. So we equate this to c. Therefore, s plus sy plus y squared is equal to c. So this is the general solution for the exact differential equation. I hope it's not difficult. Trust you understand it. Very good. Let's see if we can get our third example. Wow. Alright, so we look at our fourth example, alright? And this is referencing from the book of First Differential Equation from a book written by Dr. Ali and Professor Asid. This is one of the editorial questions. So let's look at it. In fact, if you haven't buy one of the books, make sure you go and get it. It's very nice. It's very nice. All right. So let's look at the solution to this question. So first of all, we verify whether it's exact or not. No, not as respect to x. Always this is the confusion. So we treat s as constant. Here we treat y as constant, but there is no y here. So this is going to give us 2x. So this is exact differential equation. By now, we all know how to identify or verify whether it's exact or not. So we move on to solve our differential or exact differential equation. So let me clear all this. Now we know that this is the same as the partial derivative of u as respect to x, which is 2xy, partial derivative of u as respect to y, and that is x squared minus 1. Alright, so having this, then we now go and find ux comma y, which is going to be the integral of 2xy ds. Alright, and this is going to give you, when you integrate this, we treat y as constant. So when you're treating y as constant, it's like this. When it's just like we're integrating this. So you're going to get s squared over 2. Then you attach the constant to it, which is 2y. So this cancels this. Alright. Plus g of y. Then we get u, because here we are treating s as y as constant. So this is a this as constant. So we are integrating s. What is this? That's it. So we get f square y plus g of y. Then we move on to take the partial derivative of u as respect to y. That means that we are treating s as constant. So here we get s squared plus g prime of y. And total derivative of partial derivative of u as respect to y is exactly what we have here. And that is s squared. In fact, it's not difficult. Oh, how you are laughing? I trust you. So this is this, then repeat this part. This will clear all this. So g prime of y is going to become to -1. So when you integrate, then we get this. Don't add plus. Don't add plus. So we have g of y is equal to this. So that means that whatever you see is replace that by it. Now it's negative y, so minus y is equal to c. Therefore, s square y minus y is equal to c. It's the general equation. In fact, it's not difficult. In fact, we can solve as much as possible that you can, right? But let's assume that we have an initial condition giving us that y of 0, then 1. So when you get to this side, since you have the initial condition or the initial value, this means that s is 0, y is 1. So when you reach here, s is 0 from this. S is 0, the y is 1, minus 1 is equal to c. So this means that c is equal to -1. So you just got to replace. That is all. Anyway. Alright, so that is how we do such questions. Now we are left with 2 questions to go. Make sure that after writing on the board, you pause the video and try it on your own. Alright, I believe you pause the video and try this question for me, okay? When you are done, come back and look at the final answer in case you are there or not. Okay, so the partial derivative on the that's going to be the one attached to this. Just simple, okay? Take a partial derivative. In fact, it's exact. I don't want to go behind that. It's exact. So I'm going straight to the point. It's exact. So let's move on and go out. Or in case you want me to show you how this is going to be exact. Or in case you want me to show you, then let's do that. So we treat S as constant. So this is going to give us when you get to this side, y is the function, this one too is the function, the argument is this. The argument this. So we treat it as a product rule. So leave this, differentiate this. You want to differentiate this. You differentiate cos, you get negative sign s y. Then you differentiate the inside. And when you differentiate the inside, don't forget the s is constant. So when you differentiate the inside, you are going to get only the constant s. Here, negative here will be here. So this and this, you get s y sine s y. So that is what we have for that part. Now we move on to this part. But we need to identify the n. So here we treat y as constant. So this is going to be a production. Alright. Oh, I think we are left with something to add up to this side. When you are treating this as a product, you leave this, you differentiate this. That is negative cos, negative sign sy. Then the inside is s plus snx plus here we are leaving the whole of this to differentiate this. That's going to be left with cos sy. Very good. So here this affect this, you get this for this side. This one affect this, we get minus. Okay, hope you can see that. Then get cos sy. So that is what we have for that. Let's move on to this. We are all tired. Now let's move on. Alright, here we treat this one treats a product, we treat y as constant. So leave this to differentiate this. And this is going to give you 2 e raised to power 2y plus here you leave the 2y, sorry, the 2x. When you leave the 2x, then you differentiate. Oh, we have left the 2x here to differentiate this. Oh, then let's differentiate the s and leave this. So this will be 2 e raised to power 2y. So that is for only this part. Minus, then we come to this part. Product rule. Leave this, differentiate this. You get negative. You get negative sign sy. Negative sign sy plus you differentiate this, which is 1, then you leave this, which is cos sy. I hope you are going through it yourself. So this is going to give you 4x e raised to power 2y plus 2 e raised to power 2y. And then I get 4 s sine sy, and it's going to give you negative cos sy. Very good. So that is what we have there. And let's see if it's going to be exact or not exact. Alright. So this is in, but this is nowhere to be found. Let's see if there is a mistake somewhere. When you leave this, you differentiate this, the two come and multiply this. So this is correct. Plus, you leave the whole of this to differentiate this, which will be left with 2. That is correct. Minus. Then you plug this one here. Leave this to differentiate this. You get negative sign Fy. Then you differentiate the inside because it's a chain rule. So when you differentiate the inside, the constant y will come out. I forgot to bring that. Plus, then with this, we left this to differentiate this. So here, we leave this to differentiate this, which is 1. So this is correct. Alright. So this part is correct, negative 4. But here, x times y, so we're supposed to get sy. Now, the negative will affect this minus cos sy. Very good. Hey, no easy. So here, it's established that this is in. Correct? This is in. But this. Okay. Let's try and see if there is a mistake somewhere for this. In fact, with this part, to me, I can't see any mistake because we can factorize these 2 out. And even when we factor these 2 out, leave the x, differentiate this. You're supposed to get this. Oh! That is where the mistake is coming from. We are treating y as constant. So when you leave this to differentiate this is the whole of this is a constant, so that is 0. So x times 0, it's good that we take our time to do 8 one by one, plus here we differentiate the x, we get 1, then we leave this, so that is that. So let's see what we are going to get for that. So this part, this times this is 0, and this times this, we get 2e raised to 1 2y. Very good. I hope it's established. Now, you can see that this is the same as this. Therefore, partial derivative of m as respect to y is equal to the partial derivative of n as respect to x. So this is an exact differential equation. We move on to our last question, which is involving with an initial value. And you see, this is not in a proper form. We are going to show whether it's exact before we solve it. So we have to let it be in a proper form. So by cross multiplication, we are going to get y 1 minus x squared dy to be equal to this multiply this, then s y squared minus cos s sin s, is that how it is? Yeah. Yes. So we are not in the form of a total derivative. So y 1 minus x squared dy minus plus because, minus s y squared minus cos s sin s dx is equal to 0. We are now having a total derivative. So we identify our m. which is going to be this. Don't forget, the negative is part. So this is negative sy squared. This affair is plus cos s sin s. So we go on by finding this as respect to y. We treat s as constant. So here we get negative 2sy. Negative 2sy plus we treat s as constant. Beautiful, that's what I like. Everything here is zero. That is what I like. I don't want a bigger plan. And with this, our n is just going to be 1 minus x squared. 1 minus a. Sorry. Here we have to expand it so that we get it in the simple form. Okay, so here we get it y minus x squared y. Multiply these two out. So treating y as constant, we get negative 2s, negative 2s. So you can see that here we are treating y as constant. Oh, so here will be negative 2xy. So this is equal to this. So we are saying that this differential equation is unexact. So we move on to find the general solution. We move on to find the general solution. So with that one, we are going to stick to only the writing of identifying this and this. So let me bring this back. So to get we pick the one. So this is the same as the partial derivative of u as respect to s, and this is the same as the partial derivative of u as respect to y. By treating y as constant, integrate this, you get negative s squared over 2 y squared plus, when you want to integrate this, integral of cos s sin s. Here you can see that integrating of this is going to be difficult for you. So that is why it's not always that you pick, but sometimes if the integration of the m in terms of x and y is not going to be difficult, no problem. Alright? But if the integration is going to be difficult, then you have to go and use this as your integration. Because you see, integrating this is going to be something difficult for you to do. So this is the case where you will not use the one that you integrate as respect to x, but the one that you integrate as respect to y. I was looking for such example, and I think this is what we can do. We can use to do that. Very good. So you no more use this, but rather use this. As respect to y, I hope you can see that. By treating s as constant. So you get this over 2 minus treating s as constant. So when you integrate this, you get x squared, y squared over 2. Because this is constant, so you are integrating this, which is y squared over 2. In fact, it's a nice question. I was looking for such to show you that it's not always that you integrate as respect to x and go and do the partial derivative of u as respect to y. But here you can integrate as respect to y And now, this is going to be plus h of x, because the constant is the x. The constant is the x. Very good. So here, you now take your partial derivative of u as respect to, saying this as respect to y. This will be as respect to x. Let's move on. So now, we treat y as constant. So this is 0. We treat y as constant. So we differentiate this. When you differentiate this, you get 2x over 2. Alright? And the y is a constant plus h prime of x. So this cancels this. So you get negative s y squared plus h prime of x. Very good. So now, having this, then there's the partial derivative of u as respect to s. So we know that what we have in the partial derivative of u as respect to s is exactly what we are having here. The partial derivative of u as respect to s. Please pay attention to this question. Pay attention. In fact, I'm going slowly, not only because I'm tired, but because I want you to get understanding. So what we do here is that we equate the whole of this. It's going to be equal to this, and this is this. So equate it to this. And now see what you are getting. This will cancel this, because when this comes here, it will cancel out. So what do we have here? We have h prime of s is equal to cos s sin s. Then to do this, you will do it as respect to x, as respect to x. So h of s is equal to, it's back again, but don't worry, we can still do it. Alright, so here I need your idea very well. In fact, getting this in this stage is better than the other one. Alright, so getting it here is not any problem. Don't worry. It's not any problem. Don't worry. We can still do it. Alright. So integrate this, it's not anything. I don't want to clean this part because that is this. Now we know that sine 2x from trigonometry, sine 2x is equal to 2 cos s sine x. Hope you are not forgetting it. See where we are getting to. So this over 2 is the same as this by dividing both sides by 2. Therefore, to integrate this is the same as integrating sine 2s over 2 ds. Very good. And this is how that can come out. So to integrate this in the same manner, that's why you have to be good everywhere. Trigonometry, calculus 1, calculus 2, everywhere. You can go there. You can go there. Alright. So there's no integration by part. It's just your algebra to manipulate it, knowing that this is equal to this. Go away. So here we have half times. Integrate this, you get negative cos 2s. But since we're integrating, the constant in here we divide. Don't forget that. And this is going to give you negative cos 2s over 4. Negative cos 2s over 4. So this is h of s. H of s. So now that we have h of s, we now come and finally we are done. We now come and do the substitution. So therefore u of y square over 2 minus x square y square over 2 plus this is what we have here, which is negative cos 2x over 4 equal to c. So that is our final answer for this question. But please remember that we have the initial value here. So what this means is that x is 0 and y is 2. So please, for that one, do that and find your c. Okay. See what you are going to get for that. Thank you. Yeah. In our next video, it's going to be interesting. Wow, it's going to be interesting. And that is the interesting part that I like. And we are going to look at the case whereby when in our next video, we are going to look at the case that when you verify, it's not going to be exact. So if it's not exact, it doesn't mean that you can't do anything about it. We can do something about it, and that is integrating factor. So for that one, we will go and find the integration factor and use it to come and undo it for it to be exact, for us to continue to solve our general solution. So you'll be looking at that one. That is integration factor. See you in that